So guys, again, thank you a lot for coming. It's a huge pleasure to join you guys here today. I'm going to present here just a big picture because the main intention here is to show you what we have done there in Brazil from my university, and then I would appreciate a lot if you could see some overlap so that we can maybe do something together. So the main intention here is to show you what we have done and what is new coming from there. I mean, new research, etc. So, well, we're going to see now a brief presentation of Unesp, which is my university, and then an overview about some finished and ongoing research on urban water. Well, Unesp is one of the São Paulo State University. We have three universities in São Paulo State. Unesp is one of them. And São Paulo State is, I don't know if you can see my point. My, let me see if I can. Well, I'm not in the presentation mode, so maybe, can you guys see my mouse pointer? Just to make sure if you, okay. So, oh,
I sometimes also can see.
can you see my mouse pointer? Just moving around to.
Yes, I can see it.
Okay, thank you very
Yeah.
much.
Okay.
Thank you very much. Here is São Paulo State in the Brazil. So this is the southwest part of Brazil. As I said, Unesp is one of the university of the São Paulo State. I'm settled in this part of the state, in the more or less in the middle in the state. It's called Rio Claro, the city. But the whole university has something like 24. Is in 24 cities and has about 34 institutes spread off in São Paulo state. So it's a university which is settled in many parts, many cities of the São Paulo state. So there we have more or less, these numbers are not completely up to date, but it was the numbers from 2019. But we have more or less 150 graduate programs with 14,000 graduate students and 40,000 undergraduate students. We have a little bit more than this now, but it's around 2,600 teachers and researchers. So we have there are a sort of courses and covering from humanities to social sciences and physics and, well, mathematics and all sort of engineerings and etc. Well, as I said, particularly I am in Rio Claro, Institute of Mathematics and Geosciences, and we are going to show you guys what we have done from there. Well, there are two main research fields that I'm responsible for from there. One of them is connected to urban drainage. We're going to show you what we do in this field. It's more or less basically regarding some drainage modeling and SUDs. And there's another field which is water treatment, specifically drinking water treatment. So there are kind of research that well, this kind of research we call like demand-driven research. This demand-driven research is based on the interest of municipalities and community on solving some specific problems. So in this case specifically, is just an example, but in this case specifically, we were interested in seeing what we could do to simplify the urban planning by using common, I mean, out-of-shelf programs softwares, out-of-shelf softwares, where we can identify easily the point where flood can occur without using that complicated mathematical models behind the modeling drainage systems. So we try to see how we can use, for example, in this case, specifically the terrain digital image to identify the main points of floods in the city so that we can plan better the city, the occupation in these areas. So here we basically validate the software for this purpose. So we run in parallel the complete drainage modeling and then run the simplified terrain-based modeling and or just to see if the things math, and if not, we just correct the things in order to see how they can be used easily used for municipality to for as a decision support for urban planning. This is another example of demand-driven research. It's very common in Brazil, for example, that city are still growing. So when city grows, what is common is that it grows in the outskirts, basically because the center are pretty dense or because the center terrain costs a lot. Lots are very expensive. So sometimes even social programs for uh, poor people put this kind of new areas, new urban areas in the outskirts, which means that there is an interface between the rural and the urban areas. And in this area, these are very sensitive areas for some environmental problem because well we have this kind of modification of the pavement, impervious pavements, etc. So these are potential areas for erosion, and well, we have this kind of ravines on those things. This just for you to have idea, this is a huge ravine we have here. I can't remember the extension, but it's pretty long. But I remember the height. The height is about 40 meters. So it's a huge ravine, and the common practice for this case for energy dissipation and other things to avoid soil lost are not fitted in this case because the soil is a little bit sandy, so the subsuperficial flow uh, result in some soil lost, and the entire area have a problem with the entire area sank. It's a kind of subsidence problem apart from the erosion problem. So that well, normal practice wouldn't work in this case. So we identified what happened and propose a new uh, a new approach for this kind of problem based on the subsuperficial drainage instead of the common this kind of cut stairs slope which were commonly applied there. Well, another kind of research that we have there in partnership with Federal University of São Carlos, which is based 60 kilometers from my place, is a experimental catchment area. In this experimental catchment area, we basically study how suds behavior in terms of flood control and in terms of pollution removal. So we are there interested to see in the catchment scale how stormwater can be uh, stormwater effects in terms of floods and pollution can be mitigated. So we hear this is an example of a real scale study, a real scale application. It's not easy to keep. It's not easy to get results. Sometimes experiments, the results are not so consistent in terms of trends, but still with real scale. So we are very interested in this kind of research and struggling to keep this because it's very expensive to keep this kind of research. But then still, in this kind of research, we investigate something like infiltration trenches, um, soak wells, and grass canals, infiltration plains. I mean, all sort of SUDs that are possible to be deployed in this area. We are interested in seeing how they perform. So in this case, for example, particularly, we were interested in seeing how pollutants in terms of suspended particles could be removed uh, in a convenience structure. I mean, instead of using the common canal, which are in previous area, in previous canal, we just replace this cement by grass, and then replacing cement by grass, we are interested to see how water flows in terms of in order to meet the hydraulic criteria, but not only in order to see how particles could be removed in the way during the water flow. Okay, so this is a kind of research. This is a huge canal. We use is about 100 meters long. We use this to transfer water from one place, which is another substructure, the infiltration plant, to another place. So as an overflow structure. So we wanted to see there how they behave. So we got samples several from several parts of this canal, and we measure suspended solids, and we model how suspended solids could be removed along this structure. Well, the same research are being performed with this kind of filtration trench, which is basically comprised of infiltration plan. It's a kind of filter of grass, and then the infiltration itself, where we have some filled with different stuff. I mean, some rocks, sometimes can be tires, sometimes can be we can change this to just fulfill in the infiltration trench to see how it behaves in terms of flood control, but also in terms of pollutant removal, particularly suspended solids. We also deal with some kind of green roof, where we are interested, a part of seeing the well-known benefits of green roof regarding the green area, the temperature control, and those things that everyone knows. We were interested in seeing how we can conjugate green roof with rainwater system. But well, this is something that we did in the past. It's not working right now, but well. So this was some research in real scale and some prototypes, and we also perform some lab scales in this area, in urban drainage area. So here we studied like how urban pattern could influence the soil erosion and this aspect. This was a partnership with University of Coimbra, Portugal, and there we were interested in seeing different arrangements in terms of urban occupation and their influences on soil erosion and peak flow. This is in a lab scale. Well, again, still in the lab scale, we were interested in seeing how pavement cover could change the flow condition and also the spread of contaminants. Here, we were interested in seeing how velocity developed in this very shallow flow, changing the pavement, but also how this structure can be used um, to disperse pollutants, to disperse dissolved pollutants, so that the pollutants they are in liquid phase. Um, Sometimes we have some, like for example, oil or something that leak in the catchment area, and how this in liquid phase can be spread in order to be uptake by the substructure, because these are convenience structures. I mean, the structures which were used to transport water from the catchment to the suds. So these are the example of some lab research also, where we were, as I said, interested in seeing how the dispersion coefficient is influenced by the pavement type. So we studied several pavement types and several conditions to see how, in this case, a liquid phase pollutant can be dispersed for during the transport. Well, something like a connection between drainage area and water treatment is, I consider something in between, is rainwater harvesting. Rainwater harvesting is part of our interest, and we were there interested in collecting water, in harvesting water from roof, and see how we can use this water and how this water can be treated, how the reservoir, how is the best way to design the reservoir. I mean, specifically the sizing, because the reservoir is the most cost part of the system. So it's the most expensive part of the system is the reservoir, especially for low-income people. So in these low-income households, the reservoir can be a very obstacle to rainwater deployment. So we were interested in treating reserve, and also we were interested in seeing how the rainwater harvesting can affect the design of sewage collectors. This is because, for example, when you do when someone do a project in sewer collectors, they adopt a certain amount of water coming from the the water system, the common water system. Once you drag water out of the water supply system, which is the only part of the system which is measured, the municipality or the company responsible for managing the water, they cannot see anymore how much water is being consumed, because it comes from different sources. So here we were interested in seeing how this may affect the sewage uh, um project, and how this may affect the bill at the end is how it may affect the bill. I mean the taxes and the tariff for water and wastewater. Well, another still in rainwater harvesting, we we normally we did this partnership with. We are open to do another partnership with some African countries, looking at how we can easily treat rainwater, but here for drinking purpose. So this is another challenge. This is something completely different from the other research, where uh, rainwater is used for non-drinking purpose. Here in this case, for drinking purpose is much more dangerous. We have to be very carefully on this, because it's a matter of public health. So this is another approach we did with some partners from University of Redford. Well, from urban drainage and rainwater, now we are going to water treatment. So from water treatment, we basically study technologies for water coagulation, flocculation, and pollutant removal by solid separation process. We are very interested in particle aspects, how particles form, how particles formation can influence in the separation performance, and how we can optimize the particles in order to make the separation process more efficiency and less cost. So this is the main idea of this research. In this case specifically, we were investigating some. This was part of my PhD, so it has been finished long time ago. But we were interested in seeing how dissolved air flotation, which is a separation technology, which applies microbubbles to remove pollutant. So we're interested to see how the interaction between bubbles and particles could be optimized in order to, well, to make the removal better and less costly. So to make the technology affordable. If I'm going very fast, just let me know, please, because I now just can only see my screen. I cannot see you guys there. So please, free, completely open to interrupt me whenever you you want. Okay. So here we have another kind of work. There is it's a pilot plant too, but it's also lab scale. So here we are very interested in seeing how flock formation interferes in the separation process, but specifically how the energy dissipated in water during the flocculation can modify flocks in terms of size, in terms of shape, in terms of porosity, and how these, the next steps, can influence in the subsequent separation process. So, well, we basically apply image analysis in this kind of research. We use some non-intrusive equipment in order to get images from the experiments while you're running without taking samples, because we are a little bit concerned of taking samples of flocks once they are very fragile and can break or modify their characteristics during the sampling. So these are basically based on image analysis. Well, the next one is the way we treat some data. For example, here we were interested in see how fractal uh, behaves varying flocculation conditions. Fractal is a shape measure, so in fractal may affect how it's related to porosity, it may affect how flux performs during separation process, or even how flux can capture some contaminants from water. So we are very interested in hearing how flocculation affects shape and how this may also affect, for example, flux strength, because well, flux are very fragile, as I said before, but because it's a intrinsic characteristic of the flux, they are really fragile, but they should be at least resistant for to passage in some apertures or orifices and holes that we commonly have during the water treatment process. So you were interested in seeing how this flocculant shape, energy dissipate during the mixes, how this can affect flux strength. Well, still in the same area regarding aggregates and flux, and we were interested to see how flocculation time affect the flux shapes. So here we can see a time scale and how flux change during the process, keeping the same energy in the water. So yeah, we're here just investigating this aspect of flux, because depending on the flux structure, I mean, if they are more compact or if they are more fluffy, the characteristics of flux in terms of strength and separation change a lot. So it depends on depending on the technology, this can affect the performance of the subsequent technology. Well, here example, for example, how flux shape and size affect the separation performance in terms of sedimentation. Here we can see in this chart in the down right side, we can see how different the drag coefficients, which was basically responsible for the resistance of flux during the settling, how it can change according to the flux shape. Here we have a theoretical modeling in the red line, where particles are assumed to be perfect spheres, and then the real flux, where particles are obviously not perfectly sphere, as you can see here just in the middle of the slide. So this porosity and this irregular shape affect the flux settling, and according to the energy and the amount of coagulant that you have to add for coagulation, and the energy you dissipate in water to form flux, these behavior changes. So these are basically our interest in this kind of research, how porosity and shape and size and etc. can affect, in this case, settling velocity. Well, here we're going to see now some ongoing research. There are some research regarding microplastic. We are very interested now in this emerging pollutant, and then we have two approach for this kind of research. One of them is based on the assessment. We have to understand where these microplastics are coming from and how we can avoid them to go into the environment. So this basically in our research in these terms, we basically are interested to see how stormwater, how much stormwater carries of microplastic, and specifically also not only microplastic but tire fragments that come from tires, from the abrasive contact between pavement and tires. And well, this is a research. In this kind of research, we use we use to investigate microplastic in these big reservoirs we have there in São Paulo. These stormwater detention reservoirs. These reservoirs are responsible for flood control. So it's a good opportunity for us to get sediments from these reservoirs because they are empty after a storm. So we can go there and collect some samples. So we collect samples from this reservoir. We are investigating microplastic and trying to characterize microplastic in this kind of reservoirs. Yeah, this is the same. We have 150 reservoirs spread out from São Paulo city. They are very huge structures. I mean, sometimes they can have 10 meters, 10,000 square meters of area, for example. So they're very huge structure, or even more. So they are very huge structures in order to contain rainwater in terms of flood. Well, I'm going to present you later just another kind of research with microplastic we are interested in, but this is basically for assessment. This is the basic one. Well, there's still new work in progress. It's not as new. It's a kind of we are 1 year or something investigating this kind of mixture. They're called fractal mixers, we are interested to see how these fractal mixtures behaves in terms of flocculation. As I said before, I'm very interested in flocculation. So these fractal mixtures can, for example, consume less energy, keeping the same dissipate energy in water. Actually, the way they dissipate energy in water is a kind of different, and this different way of dissipate water interfere in the flock formation. So we are very interested to see how these fractal pedals perform during flocculation in terms of those parameters that we monitor during the flocculation. I mean, the aggregate ones, size and shape and porosity and those things. So this is an ongoing research. We are studying here not only clay particles, but as we're going to see in some minutes, we are interested in microplastic and algae. So we are applying this for flocculation of this kind of pollutant. So here we can see how the different, just for it to have a picture, how these different pedals can behave differently in terms of aggregate characteristics, I mean shape and size, etc. And after that, as I said before, after that we are very interested to see how these particles, can be removed efficiently during the settling, for example, but not only during the settling. We are also interested in another separation process like solvent flotation, as I said before, but also filtration, which is the next solid separation, the last solid separation process in the drinking water treatment. So here we are very interested in seeing individually, I mean, flock by flock, how shape, size, and porosity affects terminal velocity of flocks. So yeah. Well, another research we are very interested is a kind of, this is another partnership. In this partnership, algae are used to carbon removal in the wastewater treatment, and then they are separated in order to use them as a fertilizer or for biofuel production. So here, my part in this project is to optimize the separation process using algae. So that's why that flocculation studies connect with this algae studies, and also with microplastic. So now, in this current research, which was recently approved, by the way, I'm very interested to see how algae and microplastic interact or separate or interaction, and how flux behavior in terms of settling velocity with these primary particles, algae and microplastic. So here we are interested in seeing microplastic removal and algae removal. Okay. Well, the last but not the least, we are also interested in seeing how some functionalized how functionalization of choline can affect, for example, some phosphate removal from urban sewage. So here in this research, we are seeking a way to remove phosphorus and separate phosphorus from sewage as a tertiary treatment. Well, we're still in microplastic. It is another research for microplastic removal, focus on flocculation, that was recently published with my colleagues from UCL. Well, thank you very much. I hope I could present you a big picture of the research we are developing there, and I hope you guys can see some overlap so we can contribute in the near future. Thank you very much for this opportunity, and I'm open for questions that you may have.